Okay, so let's have a look at some results. So the first experiment that we did is just as I described. We made some random graphs, random initial graphs. We did a number of evaluations, 3,000 for PPA, which is 120 of those generations of 10 individuals in a row. And you can clearly see that the number of recursions goes way up, and the graph really transforms from a hodgepodge jumble to a very densely packed graph that consists of two parts. And this effect was actually so strong that the similar graph, you can see how much they are alike, came out for all the sizes in our experiment. And all these graphs are non-Hamiltonian. They do not contain a Hamiltonian cycle. So we devised a second experiment before submitting this paper. And that second experiment entailed forcing the graphs to have a Hamiltonian cycle, because in the end it's a decision problem. It's an NP-complete decision problem, meaning that the previous instances all have a no answer. No, there is no Hamiltonian cycle. And we also, because the decision problem has two kinds of instances, yes instances and no instances, we also wanted to know what the hardest yes instance looked like. And so that's why we did the Hamiltonian bound experiment. So we just put this Hamiltonian cycle in, unmutable. It could, all the mutations were the same, except for that these edges in the Hamiltonian cycle could not be moved, could not be deleted, could not, the Hamiltonian cycle had to remain. And surely enough, after a number of evaluations for the plant propagation algorithm, but this also worked for the hill climber. We just used both of them, and I'm only showing the plant propagation. These graphs became harder, much harder, but they didn't show the same structure as the non-Hamiltonian graphs. It was a very big difference, right? And this graph here really is a telltale sign of those results and the difference between them. So what you see here at the left-hand side is the unbound experiment. Results, all non-Hamiltonian graphs. And of the 20 runs of plant propagation, 18 times the same graph was found. And for the hill climber, 17 times. For a larger graph, 14 out of 20 were found, converged on the same graph. And for the hill climber, 10 of 20, right? So this would appear that these graphs are actually the hardest for the exact algorithm that we used, because these are all independent graphs. But the remarkable thing is that for the Hamiltonian bound experiment, in which the graphs needed to have a Hamiltonian cycle, remember, the unbound experiments were all non-Hamiltonian instances in the end, not because we programmed it, but that's just how it turned out. But for the Hamiltonian bound experiment, these results were far less conclusive. So we have some good explainable results on the non-Hamiltonian side, but not on the Hamiltonian side, because those graphs are far less converged onto the same graph. And we don't steer these algorithms, they just steer themselves, right? And then the number of iterations, which is the of recursions required, which is this nice wobbly line here, shows a very, very regular exponentially increasing. This is logarithmic scale again, exponentially increasing trend, where it also does for the Hamiltonian bound experiment, but it's a little messier. And all in all, it just doesn't look very converged, right? And now the second really, really interesting result of this investigation is that for both the Hamiltonian bound and the unbound experiment, graphs that were found were very, very dense. And this somewhat contradicts all the older findings of the hardest graphs since the 90s being on the Komlos-Temeredi bound. And remember, we started with varying densities. We started with 100% edge density, but also with 0% edge density. And everything just went straight into this very, very dense little place with similar kind of graphs, these wall and cleek graphs, which can also look like a hamburger, like a cleek in the middle or on one side and some very sparse surrounding edges. And when Joeri Sleegers, the first author of this work, who basically did all programming and the experimenting, first gave his first presentation on this topic, he actually said, I expect this red non-Hamiltonian sleeve on the left side to basically extend all the way up into space and leap all the way over these green Hamiltonian instances. So that's basically, that might be what the problem space looks like. So what we still need is an explanation for why those Hamiltonian bound experiments did not converge. And the answer for that also comes from this Cumulus-Temerity bound. At least this is one answer that we came up with. It might not be the right answer. It might be, this is open for discussion, but let's see what you think of it. So this Cumulus-Temerity bound, this inflection point, which you can see as the pivotal point of the probability graph, is a logarithmic metric, right? And the number of edges is a quadratic metric. So as graphs get bigger, this inflection point gets moved more to the left in some way. Yeah. So that means that the number of Hamiltonian graphs in all of the state space of a certain size graph for 14 edges or for 25 vertices or for 50 vertices, that the number of Hamiltonian graphs greatly outweighs the non-Hamiltonian graphs. But still, the non-Hamiltonian graphs are harder. And the effect is even more dramatic, and I just calculated it for this single instance here. So you can see that the here right in the middle is there's only one graph which has 0 connections, which has 0 edges. There's only one graph that has 91 edges. But there's a zillion ways of installing 45 edges between these 14 vertices. So there's, just combinatorially speaking, many more graphs in the middle. So actually, this whole area, which is full of Hamiltonian graphs, and there's some non-Hamiltonian over here, is way more dramatic, should be multiplied by this area over here. And I did that actually, and you need some special programming to do that because these numbers are really big. And I calculated it, and even for 14 vertices, just 14 vertices, and remember this effect becomes more dramatic as graphs grow bigger. But even for this small number, already 93.4% of all existable graphs has a Hamiltonian cycle in there. So this means that if you confine your algorithm to the Hamiltonian cycle space, to the graphs that need to have a Hamiltonian cycle, that space is about 13 times as large as the space that has non-Hamiltonian cycles in there, right? And since those are harder, algorithms tend to go that way. So this might be an explanation why it didn't converge. Now there's one more added feature that we investigated, and that is for the non-Hamiltonian graphs, which are this ones. These are the Hamiltonian just for comparison. We investigated the 1-bit neighborhood. So what would change for a problem instance if we change 1 bit? How big is the effect? So here, down here is the hardness in recursions for this exact algorithm that we use, and the effect can be quite dramatic. If we remove any one of these edges, the problem instance becomes slightly easier, anywhere between a few percent and 30%, measured in number of recursions. But the effect is much more dramatic if we insert an edge. If we insert one extra edge anywhere in this very hard non-Hamiltonian cycle problem instance, it immediately drops down to the easiest Hamiltonian cycle instance. Your algorithm cannot go wrong if you insert one more edge. So from a no instance, it goes to a very easy yes. For a very hard no instance, it goes to a very easy yes instance. And this is a very interesting phenomenon, we feel, because the algorithm we use, the exact algorithm, seems to dominate all backtracking algorithms. We have to do a little more research to be absolutely sure. And for these algorithms, it turns out that the hardest no instances and the easiest yes instances are just one bit apart, one bit of information. So with a little bit of fantasy, you could say that the density of these graphs are somewhere in the space of self-organized criticality in a way. They just pile up and pile up and pile up until they cannot have any more edges. So what are the key takeaways for this investigation? And again, we have to do more research with more heuristics and bigger graphs, etc. But what are the takeaways, the key takeaways for now? Is that the hardest instances of this problem are all non-Hamiltonian. That they are regular in a way. And this is also a reason, and I didn't go into it, that they didn't show up in these earlier randomized ensembles, because they are structured. It's kind of a hard argument. I'll leave it aside. But they're regular. They're structured in a way. They are far away from the convolute stimuli bound, and they are just one bit away from being very easy. They're very tightly, very dense. They're up to maximum density, and the Hamiltonian cycles are much. The Hamiltonian instances are much easier. They're much more unstructured, and they greatly outweigh the number of Hamiltonian instances. But then again, this might be the reason that those algorithms didn't converge and our results are inconclusive at this point. I would say they are inconclusive, and we need to do more to unmask these, to identify these hardest Hamiltonian instances. Okay, so that's it for me. Thanks very much for watching this video. If you have any questions, just reach out, especially if you see this on social media or whatever. Just throw questions in the comments, or send me an email, or give me a phone call, or drop by my house. No, don't do that. Or I don't know, Twitter, Facebook, whatever you find necessary. Make your own little movie and post a movie comment. Anyways, thanks for watching, and for now, I'm out.